So thanks everyone for coming here this morning. It's a pleasure that we are gonna hear a little bit more about all the project that Valentina was working in the last several years on for her PhD program. So, and I usually try to, and I will do it even briefly today just to make sure that I don't get distracted too much and go to the point. But as it happens with all the students, each one brings something different. And then Valentina has been in our team for several years, growing from moving from a master's degree, then immediately to a PhD. One of the big traits that I recognize on her is usually that persistency and willingness to get things done, hardworking individual, so easygoing. So it has been always a pleasure to interact with. I know that we're gonna continue working together in other things in the coming years, which is exciting about perspectives on things that she wants to do. She's always willing to help people, which is very nice. And it's one of the traits that I really appreciate from having in our team, because that's the difference, what I say all the time, between having a team versus having a group of people that they just work individually versus a team, which is when someone needs some help. She was always willing to give an extra time and help everyone. So yeah, has been awesome to have you here. So as I mentioned to everyone, now is the time to relax and just enjoy and tell us a story a little bit about what you found in doing your PhD. So thank you.
Thank you, Ignacio. Okay, good morning, everybody. Thank you for the patient wait. But we can get started now. So the presentation today will be about an overview of management and environmental characterization of soybean yield and quality, mainly focusing on the US. So to start with the productions, oilseeds around the world, every year we produce around 700 million megagrams, of which 62% are soybeans. Soybean seeds are important for its oil and protein concentration. They have around 20% of oil and 35% of protein, which turns soybean an important source of protein and oil. So soybeans are the first leading source around the world of protein meal and the second leading source of oil after palm oil, but palm oil is not an oil seed. So now going to the US, the country that we will be focusing today. The US is the second producer of soybeans around the world. It accounts for around 30% of the seed productions of soybean, and is the second most important crop in terms of production after corn. 55% of the seeds that are produced in the US are crushed here. Soybeans are crushed to separate the protein concentrate that is called soybean meal and the oil. The soybean meal is used mainly as an animal feed, and the soybean oil is used in human consumption and for biofuels. And even more recently, we will be talking a little bit more about that later. So one of the main targets of the industry mainly is the soybean seed quality in terms of protein concentration to obtain high yields of soybean meal and oil concentration for the oil part. So that was the target for the industry, seed quality, but for the farmer, the target is still seed yield. And in soybeans, yield is rather stable compared to other crops because it has a large growth plasticity in terms of node number and branch growth that allows to have a similar yield under more or less wide range of environments, mainly plant densities. And the second target, as I mentioned, mainly for the industry, is the seed quality in terms of protein and oil, and variability of seed quality is large, mainly to complex interactions of the genotype, the environment, and the management. So soybeans, I said, are really plastic in growth. I will explain that a little bit with an overview of the crop cycle. Soybean growth starts in emergence, and vegetative growth goes until flowering, which starts in R1, but continues until later in the season around R5. So that means we have a huge overlap of the vegetative growth with the flowering period period and so on. So during the flowering period, we start to set our pod and seed number. And later in the season, we define our seed weight in the seed filling period. So this huge overlap between vegetative and reproductive stages gives soybean a huge growth plasticity. We will be talking a little bit more about that. An overview of the chapters that we will be seeing today. I will present 3 chapters. In the chapter number 2, I will explore different row spacings, focusing on an old and a modern genotype and trying to see effects on yield and seed quality on branches and on the main stem, trying to differentiate that. In the 3rd chapter, we are looking to a multi-stage project where we're collecting seed samples on farmer fields across multiple states of the US. We will try to explore the variability and define regions for quality. And in the 4th chapter, we will use that same project to try to do predictions of soybean and try to extrapolate those predictions to the soybean fields in the US. So let's go with the 1st chapter, which is number 2. This chapter is published in Lyon. And as I mentioned, we will be looking to two genotypes in different row spacings. So row spacing is a management practice that mainly affects the time of the crop for canopy closure to achieve 95% of line interception. So in that picture, you are seeing a narrow row. This is around R4 in the crop. You'll see that the narrow rows, this is 38 centimeters. They can close the canopy versus a really wide one of 1.5 meters, it cannot. So the expectation with narrow rows is that they can increase yields, mainly under limited conditions that will restrain the crop growth. I said we are exploring also an old and a modern genotype. All genotypes usually have a lower yield per plant, and they have lower branching, so it's a small plant with just 1 branch that you are seeing there. And modern genotypes have a higher yield potential per plant with more branch growth, and this allows also for a decrease in the seeding rate and maintaining the yields, or even increasing for sure. So our question here was, we know that modern genotypes have a higher yield, but can we explore differences in the plant architecture in old versus a modern genotype? Our hypothesis was that the modern genotype with a higher branch capacity have less yield penalties associated with increases in row width, and also with potential variation in seed quality in the branches and in the main stem. So the first objective was to evaluate the yield and seed quality of these 2 genotypes and their varied row spacings. And the second objective was to evaluate those differences in the branches and in the main stem. So let's now go to our methods. The field experiment that we conducted was for 2 years in Manhattan, Kansas, during 2020 and 21. We had a split plot design where row spacing was the main plot treatment and genotype the split plot. We evaluated 2 genotypes, the old genotype released in 1980 and the new one released in 2013. Both are pioneer genotypes, maturity group 3.9 and indeterminate. So the row spaces we evaluated 20 and 40 centimeters. This will be called the narrow row spacing, and 76 and 1.5 meters, which we will call the wider row spaces. So at the end of the growing season, we collected yield and we collected plants separating the branches versus the main stem to account for the yield and the quality coming from those 2 parts of the plant, branches and main stem. And in addition, we also counted the number of pods that were coming from the branches across the nodes of the main stem. So briefly, we had a strong year effect. In the first year, we had a later planting date with less precipitation compared to the second year, which turned in lower yields in the first year. So we will be analyzing both trials separately and seeing the results one by one. So these are the narrow row spacings, 20 and 40 centimeters. This is also R4. You will see that the canopy, it achieved 95% of coverage versus the wide row spacing, 76 and 1.5 meters, which had a harder time to close the canopy. So going a little bit to the analysis, you don't need to pay much attention there, but we use GLMs to assess for the effect of row spacing, genotype, and the interaction of both for the whole plant and for the branches and the main stem. And we obtain our derived quantities using Bootstrap to resample the model, and we are evaluating differences across treatments using the median of those Bootstrap simulations, and also a 95% confidence interval of the expected value. So we will be analyzing differences with that rather than with statistical significance or a p-value. So going to the results, here you are seeing the effect of row spacing on yield. And this is the bars represent the 95% confidence interval, the black bars, but you can see the bar plot and that will tell you the same conclusion. So in 2020, I said we had low yields. It was around 2.5 milligrams per hectare. It was similar for both genotypes, the behavior. But in 2021, which was a better year, the new genotype was able to yield around 50% more, mainly in narrow row spacings. And this difference was around 1 milligram per hectare. So this color is for the whole plant or the yield at the plot level. And now the darker color will tell you the yield coming from the branches. So again, in 2020, the contribution was stable. We had no differences. So in a low yield environment, the behavior was kind of the same for both. But in 2021, you are seeing that the contribution of branches from the modern genotype was around 3 times higher compared to the old genotype. So we were looking for around a 1.1 milligram coming from branches in the new versus 400 kilograms in the old. I said that we measure the number of pods in the branches across the nodes of the main stem. That's the figure you are looking here. In the first year, they were stable, always concentrated in the bottom of the plant, but in the second year for the modern genotype, which yielded more, you can see that it has more number of pods on the branches, and they are concentrated on the bottom of the plant. So our objective also was to account for seed quality. Here you can see the effect of row spacing on protein concentration. Also was relatively stable. We are seeing less protein concentration in 2021 for the modern genotype that yielded more, so the common dilution effect. But here the main highlight is that in the narrow row spacings, here you are seeing that despite the high yields observed, the modern genotype maintained the protein levels. Now you are seeing the seed quality coming from branches, and the main highlight here is for 2020, because this was a year with lower yields. And as you can see, the protein coming from branches was usually lower than that coming from the main stem. So this was also an important highlight that we discovered here, and it could be related with the delayed development of branches and with a growing season that was not really conducive for high growth. So now the effect of row spacing on oil, it was also pretty stable in 2021 with a mean of 21% overall. But in 2021, we are observing usually higher oil, and is related with higher yields. And in branches, there was not clear differences. It was pretty stable compared to the main stem. So as a summary of this chapter, the modern genotype was able to increase yields in a good yielding environment around 50% higher in narrow row spacings compared to the old genotype. This yield increase was mainly being allowed by the growth of branches. And in that situation where we observe higher yields, the protein levels were maintained in the modern genotype. And lastly, in 2020, the low yielding environment, we observed lower protein in the branches, around 2.5% less on the branches. So let's go now to a third chapter. On this chapter, we're changing the scale a little bit. We were seeing experimental field trials. Now we're seeing more of an observational study across multiple states. We'll get into that. So I mentioned already the variability of seed quality within and across regions is high. And the inference that we can make about weather characteristic and management is still limited for allowing farmers or the market to manage for seed quality. So understanding these factors that govern the variation is really important, mainly now that seed quality is gaining importance, not only for protein, but also for oil concentration, as we are seeing policies that are targeting to increase the use of vegetable biofuels, mainly in the transportation sector, to decrease greenhouse gas emissions. So it can be polemic, but this is increasing the demand a lot, and it's putting a lot of attention on oil. So for this, we conducted a multi-state project. We collected seed samples on farmer fields across 13 states of the US. We will be looking into that into more detail. But we were collecting seed and soil, bringing it to K-State, analyzing it, and then we also collected management. So the main objectives with this project, in this chapter, was to explore the variable importance related to weather, soil, and management that was affecting seed quality mainly. We wanted to identify regions across those states with different seed quality and yield levels. And we wanted to explore factors related to the environment, but link it to a geographical gradient, because many of the variables we observe were related to a geographical gradient from north to south. So the protocol that we implemented, we developed the protocol here, and we were sending that protocol to all the universities that were part of the project. And we had a total of 13 states during 2022 and 23. We collected a total of 235 fields. So for sampling soil and seeds, we were sampling between 6 and 12 samples of seed per field. And we were also sampling many soil cores in each field and forming one composite soil sample. So I said we were collecting between 6 and 12 seed samples per field. In this chapter specifically, we are characterizing each field with a median value. So we are having only one observation of quality per field, which is 235 in total. We also collected management data through an online survey. So this was planting date, maturity group, seeing rate, etc. And we calculated, we used a crop grow model to estimate phenology and downloaded the weather data through Mesonet. And the objective with that was to summarize all the weather data for the vegetative period between emergence and flowering. Also for the early seed set period between R1 and R5, and for the seed filling period, R5 until the end of the crop, R7. So we have variables from soil, analyzing the lab, management, and weather. These are the fields that we collected. Just look to the states that are involved. Those states accounts for roughly 80% of the production of soybeans across the US. So we are covering an important area for soybeans. This is the distribution of yield, oil, and protein for 2020, 2022, and 2023. This is just for you to see that the distributions were really similar in both years. The overall mean for yield was 4 milligrams per hectare, for protein around 20.8%, and for oil, sorry, and for protein 38.6%. So you don't have to pay much attention to that figure, but we had a bunch of variables. We did a variable selection, and we narrowed down to 21 continuous variables. And now we will see to the variable importance that we wanted to assess. We use the XGBoost algorithm with all those variables. We chose that algorithm mainly because it can capture complex interactions, and it can also capture non-linear effects. So this is the variable importance for yield. We will be exploring the most important variables in a bit. But here, yield was mainly influenced by maturity group and by early season maximum temperatures. This is for oil. The main variables affecting oil were temperature and the duration of the reproductive phase. We will be also looking deeper into that. And for protein, it was the precipitation throughout the season, the variables impacting the most to quality. So I showed you a variable importance, but we should look to the accuracy of prediction in each model. For yield, we had an absolute error of around 0.5 megagrams per hectare. For oil, the accuracy was also good. We had an absolute error of around 0.9%. And for protein, the accuracy was lower. We are seeing a really low R-square, not a clear relationship there. And we can hypothesize that this is because we are not accounting for any variable related to the crop growth of the plant. Protein is more dependent on the growth and the nitrogen that it can get from the plant during the crop growth. So the model was better predicting yield and oil rather than protein. We also wanted to clusterize the regions. We wanted to look to regional differences on quality and seed yield. We use a clustering algorithm allowing for a space constraint. We use weather variables and our response variables because we wanted to have overall environment for yield and seed quality. So in this map, you are seeing that clusterization. It can be easily recognized as the north in the bluish color, the center in the purple, that it's also, we can see it's a similar area of the Corn Belt, and the southern, the US, which is Alabama, Mississippi, and Louisiana. So let's look to our response variables across each region. The yield, as expected, or tended to be higher in the Corn Belt of the US, although in the south we are observing a huge variability because the production environments in the south are really variable. They have a planting window really big in the growing season. They have more temperate weather. The oil, the main difference here is that was way lower in the northern US. This is also expected. We will be looking into some other variables affecting that. And lastly, the protein concentration. It tended to be lower in the Corn Belt, and this can be related with the higher yields that were overall observed. But one highlight here is that the protein observed in the northern of the US was higher in the Corn Belt, or at least it was not lower. And this is important because in the last years we are seeing a more similar quality between the Corn Belt and the north of the US, whereas in previous decades, the north used to have way lower protein than the Corn Belt. So we also wanted to check some of those predictors and interpret the differences related to regional gradients. The most important variable affecting yield was early season maximum temperature. So this is a maximum temperature between emergence and the start of flowering. We are seeing a stable relationship and then a drop. So at high temperatures, yield is decreasing. And this is mainly true for the south of the US. So an early higher temperatures in the early season are related with double cropping soybeans that are planted later in the season and that the early stages of the crops are exposed to higher temperatures. This was leading to a shortening of the season length and therefore a decrease in the overall yield. So that summarizes pretty much the effects we found for yield. Then for oil, here you are seeing the minimum temperature between R5 and R7, so late in the seed filling period. The effect that we are seeing here is that higher temperatures during the seed filling period were leading to higher oils. And this was mainly important in the north, where oil was really limited. And what we found here was that higher temperatures in the seed filling period were also related with the higher duration of the seed set period, R1, R5. And this was also related with when the soybeans were planted earlier within the narrow planting window that the north has. But if we delay a little bit the planting date in that narrow planting window, we will be shifting our flowering and our seed filling period later in the season, and in the north that gets penalized because the temperatures starts to drop faster than in the rest of the southern US. So as a summary of this chapter, we saw that protein concentration was higher in the northern states of the US compared mainly to the Corn Belt, which this is a highlight and a trend that we are seeing in the past years. We were able to predict yield and oil with a higher accuracy than for protein concentration. Double soybeans or planting date later in the season in the south were affecting yield. And this was mainly related to early heat stress and a shortening of the growing season. And in the northern of the US, oil was mainly limited by low temperatures during the seed filling period. Okay, so now going to the last chapter. In this chapter, we are trying to upscale the methods that we used in the previous chapter to allow for predictions with a high spatial accuracy, as we will see. So some advantages of predicting oil and protein. This could help on segregating the production or at least thinking if we can use some thresholds on quality to work differently with different qualities on soybean, as we do in wheat, for example. In soybeans, this is not done yet. This is difficult to do because variability is high, both within and across regions. So in the methods of the previous chapter, I told you that we collected between 6 to 12 samples of seeds per field. This is an example of a field in Alabama in 2022. As you can see here, there are 9 black points. Each point is localized with a latitude and longitude. So in this chapter, we are using each individual observation and to retrieve all the weather and soil data, as we will see. So our sample size is way bigger here. So I said variability in lower than regional scales is high. This is an interpolation map of the protein, of the oil, in that same field. We are seeing a variability of around 4 points in a single field for oil, and this is for protein. Also, we are seeing a variability of around 2 points in a single field. So this can give you a sense that quality varies a lot. So in this sense, satellite data offers high resolution in a space and in time to download weather and spectral indices, and that allow us to calculate vegetation indices and check growth dynamics along the season. So our objective here was to develop a predictive model for oil and protein concentration in soybeans, and then to use the crop data layer from the USDA that released every year, where we can see each of the soybean fields that were planted across all of the US. So how did we do that? Our ground truth data was the soybean seed samples collected in each field. As you can see, now that we are using each of the observations, the sample size is way higher. We are having almost 2,000 seed samples geolocalized across those 13 states of the US that accounts for 235 farmer fields. We analyze them for protein and oil, and our input data for our model, we use Sentinel-2 to calculate the green chlorophyll vegetation index. Sentinel-2 has a revisit frequency of 5 days and a resolution of 10 meters. Our soil data, we were using Polaris. Polaris, it's available in Google Earth Engine. They developed a probabilistic map of soil characteristics with a 30-meter resolution. And we downloaded here organic matter, clay, and pH. And lastly, we also use weather. We retrieve daily weather data from DAMET, which has a 1 kilometer resolution, and we use the variables accumulated radiation, precipitation, and maximum and minimum temperature. So we did some processing to that data. To the GCVI, we use a time series of each growing season. In this plot here, you are seeing an example of the time series of GCVI for one specific point where a sample was collected. We feed a harmonic regression, and our objective with the harmonic regression was to obtain the peak of the curve, which is closely related with the critical period for soybean, which is not the critical period, but around the window, R5. And we also calculated the minimum before and after the curve to characterize the start of the season and the end of the growing season. So following to that, remember in the previous chapter, we had used a crop growth model to estimate phenology. And our goal here was to have a window of the critical period of soybeans for yield and quality determination, which is around R3.5, R5.5. So using the data from crop growth, the window between R3 and 6 was a 30-day window, and around the peak of the GCVI time series, that was 22 days prior to the peak and 8 days after the peak. So we use that to define this time frame of 30 days around the peak for each pixel where we sample the seeds. And we call the period before and after the stage 1 and stage 3. So the first stage would be characterizing more the vegetative growth, the stage 2, the critical period where we define our pole and seed number, and the last period would be characterizing more the seed feeding period. And we did that to summarize the GCVI and all the weather variables in those 3 periods. So once we have those variables calculated, we use again the XGBoost algorithm. We optimize the hyperparameter of interest. We did a cross-validation for that, sampling at the state and the year level. Once we were comfortable with the model, we had our final model with a training of 70% and a testing of 30%. And after that, we wanted to do the predictions using the crop data layers from the USDA. So we implemented the same pipeline across all soybean fields of the US. We used the crop data layer to mask all of the other satellite data. And we did the predictions with a 30-meter resolution. And here you are seeing an example that we will see better in a bit. So the variable importance for predicting oil and protein. For oil, the most important variables were really similar to what we had seen before. This was related to temperature during the flowering period and also to the duration of the period, which here you are seeing as radiation, but this is the accumulated radiation, which is a close proxy to the duration of the period. And for protein, now the most important variables became our vegetation index, in this case, the GCVI, which is trying to characterize the growing dynamics across the season. So how well were the models predicting? For oil, we obtained a mean absolute error of 0.76%. This is pretty good compared to previous efforts trying to predict protein. So it could be better, but it's better than what I've seen before. And for protein concentration, we are also positively surprised, I will say. We obtained a mean absolute error of 1.1%. So I told you that we use the crop data layers to filter soybean fields. Here you are seeing the state of Kansas, and you are seeing the soybean fields in Kansas. As you can see, there's a clear trend for having more soybeans in eastern Kansas, and then way less towards the west. This is also related with the precipitation scheme in Kansas. We have more precipitation in the east and way less in the west. And actually these fields that you are seeing here, they are all with irrigation because otherwise it would be difficult to grow soybeans there. So this is the prediction map for protein. Maybe the colors are not really clear in the screen, but the red colors are showing lower protein concentration and the green colors higher protein concentration. I will play the video. What we are seeing, it's a higher trend for having lower protein concentration in northeastern Kansas, where we have higher precipitation and likely a higher biomass and a higher yield compared to western Kansas, where we would expect lower yields, and this usually leads to a higher concentration of protein in the seed. But in western Kansas here, where we are having irrigated soybeans, we are seeing really low protein concentration, which is expectable due to high yields for having related to having irrigation. So this was for protein. Now we will see for oil. The relationship could be kind of the opposite. Again, it's protein. Sorry. Yeah. Okay. So for oil, yeah, the difference is, sorry.
That's the true bond.
Yeah. For oil, the differences are more clear, where we are seeing higher yields. We are seeing a higher oil, although with a great variability. As you can see. Here I was zooming in Manhattan, I forgot to say, and there I'm going west again, and now you are seeing the color in the pivots are really green, which it's saying there's a high oil in those fields, and this could also be related with higher yields observed or higher biomass due to irrigation. So a summary of this last chapter, this model or this approach for prediction presents an advancement for oil and protein in terms of accuracy, the inference that we can get on weather characteristics on the growing season, because we estimated the growing season with a time series of GCVI, and also with a higher spatial resolution. We are seeing variabilities within field and a high variability in a small region. For the future, we could refine this framework for double cropping soybeans. This is mainly true in southern US, where the planting window is bigger, and we are having more than one crop during the growing season. This is a not so good part, maybe, of the model, the harmonic regression. It can over or underestimate the beginning and the end of the growing season, and it assumes a symmetric fit for both, for the growing season and then the senescence, which is not true in reality, but we will have to implement the model in Google Earth Engine, and this is a bit challenging to go for a more complex model. In the future, we could also combine yield statistics per county, per state, and we could have an estimate of the production of oil and protein for any geographical location. And lastly, this could influence policy decisions. I said there's many policies aiming to increase the use of oil. So this could potentially help those decisions and bridge a little bit the gap between research and policy, and where possible, try to diversify the production a little bit if this was implemented in other oilseed crops. So that's all I have for today. A summary of the chapters. In the second chapter, we saw the effect of different row spacings in a modern and an old genotype. We saw that the modern genotype would have higher yields, mainly in narrow rows, and also maintaining protein levels. In the third chapter, we characterized regions of soybean quality and made some inference on weather variables for oil and protein. And in the last chapter, we just tried to predict oil and protein concentration combining soil data with satellite data. So thank you for your time, everybody here. Thank you for waiting so long for the start. I want to thank most of the people here and a lot of people that is not in these pictures. Ignacio, I want to thank you a lot for all these times. I really enjoy and learn a lot from you and the team. The team here, Champiri Lab, it's crazy in a good sense. It's really unique, I think. And you are also crazy in a good way. So thank you. Thank you because you have been a huge inspiration for me, and I really look forward to keep working in the near future. So thank you, everybody.
Okay, so we have time for questions. We can start with some questions here, and then we can see if we have some.
I have a question regarding your last chapter, your model. Did it include any of the cultural variables such as row spacing or any of those cultural agronomic challenges? They were just all together?
Yeah, we didn't include anything. I mean, you mean in the last chapter where we predicted?
Right.
Yeah, mainly because our goal there was to use the model to extrapolate it. I mean, if the model was used, to use it to extrapolate the prediction in other fields.
Right.
And it will be challenging to collect management data in the other fields. And also in the third chapter, we were thinking to include seed rate, row spacing as continuous variables, but this was including kind of noise in the model. Yeah.
Do you have any predictions of what the use of fungicides is doing on either yield and or your quality in soybeans in Kansas? I have some experience of what it's doing in Iowa, but I'm just curious what you're seeing in Kansas.
So in the survey that we used, we collected the information of whether they apply or didn't apply fungicide. Some of them answered, some of them not. So we have the data, but yeah, I mean, I should look into the potential effect there.
Okay, sure.
So is your sense that Iowa, they use it more as a, do they always use it more when they have a disease, or they use it also as a physiological effect?
Yeah, they're using it as a PGR. Sure. Yeah, they're sold on it as a potential yield enhancement material. Yes. If you have a yield potential year, a high yield potential year.
Yeah.
If it's capped by drought, they won't bother.
Yeah.
But if it's a high yield potential year, they believe they can get good return on their investment. Yeah.
Yeah.
Interesting. Yeah.
Do you have any concepts or ideas of why you think the protein concentration in the north has gone up so much in the last 3 or 4 decades? Has it been breeding or cultural practices or both?
Yeah, I mean, I think it would be related to both. I think they have been refining the planting windows, the maturity, the genotypes that they use. And maybe the yields are increasing slowly, and maybe they're obtaining a higher biomass throughout the season. And that is allowing them to accumulate the more nitrogen in the plant and to absorb more from the soil. I think it could be related to that. Yeah, I mean, and also it's in the Corn Belt, they can obtain higher yields, and the dilution effect is expected. So if the North can catch up with using better the growing season, I think this result would be expectable.
I was in Minnesota in the early nineties and started some work on a project like this as a postdoc. And at that time, the breeder, Dr. Jim Orff, started a high nitrogen or high protein content breeding program. So I assume something that Jim did has been paying off as well.
Yeah.
Breeding organizations. Yeah. So that's good to hear the progress.
Yeah. And there has been other papers showing also similar or high in protein in the north recently.
Great.
One question.
Yeah.
On his comment on protein in the north. So in the south, you got more oil concentration, right? As I remember.
Yeah, in the Corn Belt and the south, the oil was similar and lower in the north.
Yeah, so is it worth like planting soil in that region or shifting for other crop? I don't know about if it's.
Yeah, I mean, they in the north, I think soybeans are important. They also, canola is also really important there. And I would say the north have lower oil, but maybe nobody used to care so much about having low oil. They were getting penalties on the price received by farmers for having lower protein in the past. So yeah, I mean, I think it's important for the region, but the growing window for them is way shorter, way more narrow.
I mean, for the south.
Sorry, I thought you were saying for the north.
Well, yeah, it could be, but in the south. So south, they have more less protein and more oil, right? I don't know about the price, like oil compared.
So yeah, in the south, I would say it's more high oil, high protein, and not lower.
High oil.
Yeah, it's more. I mean, it's around the average. The oil, but it's not low. The oil. Yeah, and the protein the same. Yeah.
If you were going to recommend a farmer in the south of how to grow soybeans and get higher yields, what would you suggest?
I mean, to go for a full season soybean, if they want to get higher yields, but it's just if you want to get higher yields of soybean. But overall, for the season, maybe it would still be better to have soybeans as a second crop as well.
Right.
But yeah, I mean, just in this data, the decrease in yield was really clear when you went to later season.
Right.
Yeah.
They usually make more money for corn.
Yeah.
That's the problem.
Yeah.
So you need to talk to them and say,
That's right.
they will look at you and say, I'm making more money with corn. And then soybean is the extra money, income.
The extra bonus. Yes.
So it's a bonus track.
Yeah.
So on the last project, just we are finishing this year is the last year. We are still collecting more data. So we probably will get 180.
Yeah, around 160 more fields.
Okay.
Yeah, so this last chapter, I mean, I think we have to refine it for publication, but also we may include the data of this year or leaving as a validation as well.
Yeah, I was wondering why you didn't have any locations in Minnesota or Wisconsin. I can see.
No, we don't have.
Those two southern parts of those states got a lot of soybeans in them.
Yeah.
You wonder why?
I'm wondering why. Maybe no cooperation from those universities mainly.
They feel that they're competitors.
Okay.
Having working on quality a lot and they didn't want it to jump into the wagon.
Okay.
They probably are now a little bit
Jealous.
sad
Right.
because
Yeah.
the problem that, for example, if you look at what, I mean, Minnesota has been doing in the last 10 years on quality side is working with USP soybean board now and USEC, that is the export side, is they are collecting data from farmer fields every year to develop these protein and oil maps. But that data basically is collected. Sometimes it's not georeferenced. They put it together. They just develop nice PDF maps, that they usually share with exporters, people that want to buy soybeans. But the problem at the end of the day is that nothing is getting done in terms of developing an approach for sharing that information. So I think that in some way we are ending their business,
Right.
which I don't know if they will be too happy.
Right.
But what we are trying to do is trying to democratize rather than end business of people, but making sure that we do some things that they can be more transparent and also things that they can then, you develop things that they are more interactive. This could be something that you can use it now, as Valentina was saying, like to inform export in the future.
Sure.
And also to start using historical data and start putting historical data together on studying changes on quality over time.
Yes.
That information is potentially available at the county level, aggregated, but nothing is
Yeah.
kind of a georeference like this. So
But also using historical weather data, we could have like an average quality, if you want, across the regions.
I hope that now that we're gonna move into developing more this tool and finish it, and probably next years to maintain it. I mean, I think that once they see this, probably they will say yes.
Yeah.
They will collaborate,
Right.
but it happens. So it's, yeah.
Sure.
And then one of the questions that Valentina posed there at the end of the presentation is something that we wanna work on that. Maybe as a continuation of this is to start thinking about or calculating the oil productivity. Just to start looking at how much oil is available in different sections of the country and looking at getting an estimate on that. So, yeah. It will be very relevant when we start looking at the demand that is gonna come from the sustainable oils.
Right. Yeah. If you wanted to start building oil processing plants, where are you gonna?
Where?
Right.
Where will you place the plants and how do you outsource oil in different sections of the country? And how do you start thinking about this idea of potentially moving to specializing regions of the country into being more oil versus being more animal
Or protein, right?
or protein? So, and then being more strategic on doing that. So. Any other questions? If no, we can stop here. Thanks, Valentina, for your time. Thank you, everyone, for coming.